I'm delighted to have the opportunity of talking about my research here. I'm Nengkun Yu from University of Technology, Sydney. The title of my talk is Sample Efficient Identity Testing and Independence Testing of Quantum State. Property testing considers the following question. For X in S, we want to decide whether X is in P or by local queries. Distribution testing was initialized by Carl Pearson at 1990. Who considers the question that given samples from one or more unknown probability distribution, we want to decide whether it satisfies a certain probability or not. Formula is like for X in S, we want to decide whether X is in P or X is in S minus Q with high probability. Distribution testing has attracted lots of attention in the community of ITCS. For instance, the identity testing problem, the independence testing problem, and the conditional independence testing problem. Many techniques and ideas, smart ideas comes from analyzing L2 norm. Quantum property testing. The problem is given copies from one or more unknown quantum state, we want to decide whether it satisfies a certain property. This problem was initialized by Alexander Holevo at 1970s. Different from classical property testing, we have to deal with a great variety of measurements. Considering the quantum property testing problem as follows. Given n copies of d-dimensional quantum state rho and a property P, we want to verify whether rho satisfies P or far from satisfy P. Joint measurement setting, we need to design a measurement with dimension d to the n, apply on the n copies of state rho and output delta. Delta with high probability, delta will characterize whether rho satisfies P or far from satisfy P. For independent measurement setting, we're measuring each copies of rho independently and gathering all the classical outcome from the measurements and compute data. Comparing these two sampling methods, joint measurement could have lower complexity, but the measurement dimension is d to the k, therefore it's hard to implement. Independent measurement, which has slightly larger complexity, but the measurement dimension is d, which makes it easy to implement. Quantum property testing has attracted lots of attention recently. For instance, the tomography problem considering about the outputting a good estimation of a given state and spectrum testing problem whose goal is to output a good estimation of the spectrum of a given state, and identity testing as well as the shadow tomography and online learning. Thinking about the sampling method difference between the classical property testing and quantum property testing. Quantumly, we usually use the Shewhile duality to minimize the sample complexity. But classically, the only sampling method is counting. Therefore, smart ideas and techniques from classical property testing are not used in quantum property testing. So in this work, we design an independent measurement which preserves the L2 norm. So for d-dimensional quantum system, there's a measurement M such that the resulting probability distributions P and Q for any two quantum state rho and sigma satisfy that. The L2 distance between P and Q is the L2 norm between rho and sigma divided d plus 1. And the L2 norm of P and Q are both no more than square 2 divided d plus 1. Therefore, we have the framework of solving the quantum property testing problem for L1 norm. So first we apply the measurement and transfer the problem into the L2 norm problem for classical property testing and recall the classical algorithm for L2 norm. Then therefore, according to our relation, we have a quantum algorithm for L2 norm, and therefore we solve the L1 norm by recalling the relation between L2 norm and L1 norm. So using this framework, we can have some results on the quantum property testing. For instance, the deterministic algorithm for identity testing. So in this talk, I will focus on this one and as well as the lower bound part for the joint measurement of independence testing. So for the identity testing problem, so we want to distinguish whether two quantum state rho and sigma are equal or the distance between rho and sigma is greater than epsilon. So we actually show one can show that the d square copies of rho and sigma are enough, simply because we call that the result of CDVV, who show that order of B divided epsilon square copies of P and Q is enough to distinguish P equals Q and two norm between P and Q is greater than epsilon, where B is the maximum of the two norm of P and Q to the probability distribution, together with our result. And for independence testing, so here, a two-system quantum state rho 1, 2 is called independent if rho 1, 2 is rho 1 tensor rho 2. And the goal is to distinguish that whether rho 1, 2 equals rho 1 tensor rho 2 from the rho 1, 2 minus sigma 1 tensor sigma 2 greater than epsilon for any sigma 1 and sigma 2. Actually, we only need to distinguish rho 1, 2 equals to rho 1 tensor rho 2 from rho 1, 2 minus rho 1 tensor rho 2 greater than epsilon divided 3. And then we just call the identity testing. And similar to the identity testing of collection independence of collection and the conditional independence, we have many results. And for the lower bound for the joint measurement for independence testing, we can actually show that sigma theta tilde d1 tensor d2 divided epsilon square copies are needed for independence testing in d1 tensor d2 system. So we will use this result by Ryan O'Donnell and John Wright at 2015 that 100D divided epsilon square copies are sufficient and 0.15D divided epsilon square copies are necessary to test whether rho is I divided D or rho minus I divided D is greater than epsilon. So if both D1 and D2 are very large, we can employ the independent testing to test whether rho 1, 2 is I1 tensor D1 tensor I2 tensor D2 by first test whether rho 1 is I1 divided D1 or rho 1 minus I1 divided D1 is greater than epsilon 1, and then we test whether rho 2 equals to I2 divided D2 or rho 2 divided I2 divided rho 2 minus I2 divided D2 is greater than epsilon 2. Then we test the independence of rho 1, 2. By carefully choosing epsilon 1 and epsilon 2, we can reach the goal, but it does not work for large D1 and small D2 because step 1 and the maximum mix testing are at the same order. So we think about the dimension splitting technique. So we consider 2 by D system and regard it as a 2 tensor 2 tensor 2 tensor 2 system. And we split, in other words, we split D into log D qubit system. And we can use the independence testing of 2 tensor D system to test whether a 1 plus log D qubit state rho is I2 tensor divided 2 tensor. We test each rho I to see whether rho I equals to I2 divided 2, so all far. And then we test whether rho is independent through any 1 versus log D cut. And we use the observation that M plus 1 qubit state is epsilon close to be independent for any 1 versus M partition, then is 5M epsilon close to be M plus 1 partition partied independence. And that's it. Thank you.